Welcome everyone to another of our WMCTC evening lectures, and thanks as usual to both the Royal Society of Chemistry and also the University of Birmingham for enabling these talks. Speaking of the University of Birmingham, I'm delighted that our speaker tonight is the Head of Chemistry, Professor Rachel O'Reilly at the University of Birmingham. And we're also delighted to have a very topical talk. Plastics are very topical at the moment. It's in the news and a lot of people are very interested in them, both the pros and cons. And we're looking forward to hearing, well, what are the issues and what are researchers currently doing about it, and what lessons might we learn perhaps from nature when we design these polymers and perhaps design how we may best use them. This is also the P.F. Franklin Memorial Lecture as well that Professor Wright is giving, so a double honour there for us.
Thank you very much, and thank you very much for WMCTC for inviting me to give this lecture. It's a great pleasure to deliver the P.F. Franklin Memorial Lecture, especially given Franklin's association with the University of Birmingham. As Mark said, I am the head of school here at the University of Birmingham. I thought I'd start by telling you a little bit about me, and then I'll move on to the topic of my talk, which is redesigning the world of plastics. So just to let you know, you may have picked up from my accent that I am Northern Irish, so I'm from Hollywood, but it's Hollywood in Northern Ireland, not Hollywood in America. I came over to England, to Cambridge, for my first degree. This is me in my master's project with my first sort of serious reaction that I ever set up. I was extremely proud of. I took the researcher I was working with, I took a picture of, and my mum put this picture on a t-shirt because I was so proud of my first reaction. I was making a gold cluster, and I think that's when I got the bug for science, and then I went on to Imperial to do my PhD, and the little circle there is me with my PhD with my PhD group, and I graduated in 1999. I then had the fun and fortune to go over to the US to do some postdoctoral work. So I continued my research studies both in IBM, and this picture here, if I just change is the IBM building I worked in California, and I also did work at Washington University in St. Louis. So St. Louis is best known for the arch. So I had a fantastic 2 years in the US when I was learning all kinds of new science. I then came back and took up an academic position at the University of Cambridge in 2005, and then I got married in 2008 and married an academic from Warwick, and I moved over to Warwick in 2009. And this was the building I was in at Warwick, which was a materials and analytical science building. And then in 2018, I moved to the University of Birmingham. And so I've been here for around 3.5 years, and about 3 years ago, I took over as the head of school. So I'm really fortunate to work with an absolutely fantastic group of people. This is my research group. They are from all over the world and bring amazing and very different expertise. We've graduated as a group lots of different PhDs and lots of different researchers, be that school students and visitors and summer students and everything. So we have a very wide and broad network of researchers. And these are just some of the people in the past who've given us funding to support our research activities. So all the stuff I'll talk about today is being undertaken by all these fantastic researchers, some studying for their master's projects, some for PhDs, and some post-PhD as postdoctoral researchers. But my group are fantastic chemists, but I just wanted to flag they're also absolutely fantastic bakers. So everyone says if you're a chemist, you should be a fantastic cook, and this is certainly true of my team. So these are just some of the fantastic cakes that they've made for me over the years. This was a brilliant periodic table from a number of years ago. A fully playable Scrabble board, which was amazing in cake. A fantastic cake when we published our 100th paper. A polymer, a polymethyl acrylate polymer for my birthday. And then when we published 150 papers in 2016, this fantastic cake. And then a few years ago, we published our 200th paper, and they baked as a team 200 different cupcakes. And what you might be able to see is the design on each one of these cupcakes is a picture that's taken from the paper, and it's all numbered all the way through from 1 to 200. So they're an absolutely phenomenal bunch of scientists. They're also fantastic bakers and really creative. And I think that creativity is something that's really important in science. So when they're not baking, what do they do? Well, as a team, we have, my research is really interested in thinking about how we can make and do precision chemistry across different length scales. So we do some stuff with small molecules and we do work with DNA. We do a lot of work with polymers. And actually, this is one of the things for a number of years we've been interested in, how we can use polymers as a scaffold, maybe to embed catalysts within to mimic enzymes, so things like synthetic enzymes, thinking about how we can make synthetic tubular structures, again mimicking nature, or large-scale polymer materials that have different functional properties. And for many years, we've been working with polymers, and I think one of the reasons why I think I fell in love with polymers is because polymers is quite a controversial discovery, and I think it's remarkable. So Herman Staudinger is the academic who basically founded the fields of polymers, and when he was really, at the time it seems quite remarkable, but it was really controversial when he suggested that the materials such as polymers were indeed long-chain molecules. This was against all understanding, and previously it had been hypothesized that these were small molecule aggregates that had come together, not long covalent chains. And he really was pioneering in the studies that he did. And when he published his seminal work, he was basically, the university was at, said he essentially had to leave. He was seen as crazy. Many of the organic chemists in the time really did not believe the data he had, but he stuck to his guns. He was right. He was very insistent, and he discovered the properties and fundamentally the concept that polymers are these long chain molecules. And he won the Nobel Prize in 1953 for these discoveries. And this was his seminal paper, which basically is über polymerization, about polymerization. And again, he was really a remarkable scientist because of his insight, but also his determination and the belief in the results that he was getting. But it was very controversial, which I think is quite remarkable when you think of the world in which we live in now. And this is a fantastic quote now from Guillaume Natta, who won the Nobel Prize in 1963, which he said, if our age were to be named for the materials that characterize it, as were the Stone and Bronze ages, the past, we might be known as the age of plastics. And I think this is really is very true. If you think the world around us, most of the materials we interact with and use are based on plastics or polymers. But what is, I think, always quite remarkable is that polymers are actually very much a 20th century concept. So this timeline just really tries to show you and illustrate sort of the explosion of polymers almost. So the early synthetic polymers such as bakelite in the early 20th century, then very quickly the discovery of new synthetic polymers such as polyvinyl chloride, styrene, you've heard of, urethane, nylon. As you can see, it was very interesting that the global proliferation of these sort of commodity polymers really was at the end of the Second World War. His development of all these very cheap, but also very lightweight material, very robust materials, really led to this explosion over the period of over the last century. And interestingly, I think in 1989, polymers overtook steel as the world's most used material per unit volume. And this was, again, quite remarkable. And it has been suggested, perhaps for not all the right reasons, that polymers have now become so ubiquitous in the environment. They will be undoubtedly perhaps a geological indicator for the current era that we live in, which is obviously not a good thing. But if we look at the and come back to the concept of the 21st century, which is the age of polymers, if you think of just these are some of the polymeric materials that are that we all will use and interact with and rely on, actually, be that from clothes, from packaging, tires, or major components of electronics such as smartphones, polymeric, all kinds of packaging. These are all the plastic bits of a car or polymer bits of a car that are removed. There's thousands parts. It's the light weighting and properties of polymer may make them perfect for such applications. Cosmetics, footballs, it's remarkable, and it's a huge contributor to the UK economy. But what's perhaps remarkable about polymers, I think, is that when you think about this is a plot that shows the number of million tons of polymers that are produced annually. So this was again early in the 1950s, this growth, and then this sort of explosion, millions of tons. And this is a number of years out of date. It just has continued at this rate. But we're really this growth of from in a 50-year period. What is absolutely remarkable is that the same 6 polymers account for greater than 90% of all polymers ever made. And as a polymer scientist, this is unbelievable, because we can make thousands, tens of thousands of different polymers, but these 6 same polymers are the same 6 polymers that basically account for 90% of all polymers ever made. And actually that says something to the lack of complexity and value that we put in polymers that perhaps accounts for why we have a plastics problem. So if we think about polymers and plastics, the use of, if we think about the good, phenomenal for lightweight composting materials. Air flight relies on use of polymers, and because of the light weighting. iPhones, communications, polymers are a key integral part of that. Also really important, this is an example of a stent. Polymers are actually ideal materials for such applications. So this is the good in polymers. The bad is basically just shows lots of plastic toys. So just a great gluttony of plastic materials. And this is the bad, the really ugly, and the real issue starts to come into the packaging that we actually perhaps don't need for a lot of materials, but we've become accustomed to. So plastic cups wrapped in additional plastic wrappers. This is an example of a tin of Coke wrapped in plastic and that you can purchase. Again, we wrap a number of our foodstuffs in things such as cling film plastic to try and maintain prolong the life. One of the major issues actually is black plastic, and I'll say a little bit about that later. But actually, the additives that we add into it's not actually some of the additives we add into the plastics actually are what cause us issues when we start to think about recycling and reuse the polymers. So we have a polymers problem. I think everyone knows that, and there's some absolutely terrifying statistics around that there'll be more plastic in the oceans than fish, and in the not too distant future. And as a polymer scientist, this is terrifying. I've spent my career making polymers and thinking about how we can apply polymers to solving problems, not making problems. But I think it's worth thinking about what happens to the polymers that we make, and think about why we might have a polymers problem. So if we think about what happens to the polymers and plastics when you throw them away, so you throw them away, they get picked up and they get separated, because I've told you that there's different types of polymers. They need to be separated because they need to be dealt with differently. They basically get baled, so put into large bales, and then they get processed where they get shredded. You have to move a lot of the contaminants and any metals, etc., any other additives. You process it, essentially extrude and melt, and then extrude and remold. Yeah, and this is an ideal cycle. The problems you have are to actually, a lot of these materials have various different additives in them, and the black plastic is a good example, that actually the separation processes that we currently use cannot detect what the material in the black plastic is because of the additives that we use. So our separation methods are flawed, and because of the nature of the additives that we now add into a lot of polymers, actually separating them becomes very, very difficult. So actually what happens is these processes mean that the polymers, the recycled plastic that you're forming, often has inferior properties. So rather than being able to continue this cycle many times, you actually start to lose value and lose material properties. So it becomes unviable to be able to close this loop. So you may have heard about linear and circular economies. You think of we unfortunately, I think, have our way of living is a bit of a linear economy. We take what we want from the environment, we make what we need, and then we dispose of it. And that is, as I said, not a way of living that will be able to sustain the resources we have in this world. So actually, a circular economy is undoubtedly the way we should be working. And this is where we make something, we use it, and recycle and can remake it. The challenge being that actually to achieve full circularity is actually really difficult. And the reason why that is consumer compliance is one of them. So how often do each of us, how good are we at separating and ensuring that we are recycling the plastics? The other problem is not all plastics can be recycled. And this is simply because potentially some of the additives that are added into the plastic to give it particular properties. So it ends up getting in, so that a lot of the plastics that can't be recycled get incinerated, and that creates greenhouse gases, which of course we know is not good, but also much of it ends up in landfills, and this causes further environmental problems. And just to give you an idea, your polystyrene cups that you have, that you might get a hot drink in, it will take 300 years to degrade on a landfill. For that single polystyrene cup. So these things pervade in the environment for a long time if we don't think about how we can reuse them and recycle them. I think what's really interesting is nature makes polymers, but nature doesn't have a polymers problem. So I think one of the things to think about is, well, what polymers does nature make, and why does nature not have a polymers problem? So nature makes, so DNA is a polymer, and so nucleotides, proteins. Yeah, so the fur of a rabbit is keratin, which is lovely and soft, and a protein, and carbohydrates, sugars, and these are all polymers, and nature makes them, and nature doesn't have a polymer problem. If you think about some of the polymers that we make, so polyolefins, talked about polyesters, so clothes, polyurethanes, the soles of shoes, and if we just look at the structure of the polymers that nature makes compared to the polymers that we make, you may see some differences, and this is something that we've been interested in for a number of years. If you look at the polymers that nature makes, they compared to the polymers that synthetic polymers that we make, they're much more complex. Yeah, so these have different stereochemistry. So there's different, the arrangement of atoms in space is different. There's heteroatoms in the backbone. There's oxygens. There's nitrogens. It's not just carbons. They're rings, etc. They're very much more complicated structures. We actually make, and these are three of the most commonly made polymers, these are really very, very simple. Yeah, and I think this is one of the things that perhaps we need to consider when we think about our nature's relationship with polymers is very positive, because it makes very complex polymers that have really high functionality and very high value, and it's designed them to be able to be reused and recycled. Our polymers are much lower value. They have much less complexity. They're much less functional. Polymers kind of are a very cheap, low value material that we use and discard rather than reuse. So why do we do that? Well, it might be worth thinking about the way that we make polymers. So this is, if we think about just traditional monomer synthesis, you take an initiator and a monomer, and that makes a polymer. And this hopefully video will play. So this is my group, and demonstrating the yellows are initiators. They activate, and they suddenly try and pick up lots of more monomers. They're just a random reactive end group, just adding lots and lots of different monomers. And hopefully you will see they form 4 different polymer chains, hopefully as they get into position. And these 4 polymer chains are all different lengths. Yeah, so we've been able to make 4 polymer chains, different lengths. There's no control, and this is the traditional way that we make, that synthetic chemists make these low value polymers. That's great. You can make the polymers, but they've got different length distributions, so the complexity isn't there. There was a big advance, probably now about maybe it's close to 30 years ago, about 25 years ago, where that really made a huge difference in polymer synthesis, which was where you now start, rather than just reacting an initiator and a monomer together, you have some sort of capping agent, and this is the chemistry that my group specialize in. And the idea, this capping agent actually provides polymerization control and allows you to control the number of monomers added. So you're starting to be able to start to make polymers of are better defined, more control, and start to become higher value. And this is just the chemistry that we use, where we essentially add in this little bit of this compound here, which we call a chain transfer agent, and that essentially controls the polymerization. And I've got a video to try and show that. So again, the initiator opens, and then but instantly a green capping agent adds to it, and then we are adding monomers, and the monomers are being added in a very controlled way. And then we make 4 chains, but all have all of the same length, and they all have our initiator at one end and our capping agent at the other. And this allows us to be able to add in a second monomer and make blocks and make things much more complex. And this was a huge advance in polymer synthesis, but actually still is really still is, and I still think this technology will win the Nobel Prize in the not too distant future. But actually, we're still so, this method of synthesis is still so uncomplex compared to nature. So nature, if we think about how nature makes polymers, and this example just is for how nature makes a protein. This is an image of the ribosome, where we have 2 subunits essentially that create this pocket, where we have this mRNA. Imagine this is, it's basically a coded tape, and it essentially codes for which tRNAs come in at any point and bind and add specific monomer units in the sequence control manner. And the way that it does this is by confinement. So it creates a little pocket in which this happens in, and also templation. So this important interaction that basically designates and codes as to what monomer you should add next. So this is a biological machine, and we don't have synthetic machinery that makes polymers. Hence, the polymers we make are much less complex, and this is so we're stuck with much simpler approaches. And a number of years ago, my group became quite interested in, could we actually think about confinement and templation from a synthetic perspective to try and improve polymer synthesis? And what we did was we embedded the polymers within polymer micelles, within these little pockets. And there's another video to show that now basically only monomers that are within our little the purple circles or the micelles were able to react, and all the other monomers were left behind. So rather than using conventional capping, we now started to use confinement, basically being inspired by nature, because that's how they do it. And this works really well, and actually quite remarkably. And we actually decided to use the same nucleobases that DNA uses for templation to allow us to actually template the monomers we wanted to polymerize within our polymer particles, to allow for using confinement and templation to make polymers. And we were able to make these daughter polymers that were really high molecular weight, low dispersity. And this approach is absolutely bio-inspired. And I think we need it starts to make us think much more about the methods that if we can improve the methods and complexity of the methods we use to make polymers, we can make more complex polymers. Why do we want to make more complex polymers? Well, if we quickly just look at synthetic versus natural polymers. So we think about a synthetic polymer, these are just some vinyl monomers, and polymethylmethacrylate, which is the material that is used in is basically perspex, so airplane windows, etc. Polystyrene, again, most of the packaging materials. We can make as chemists thousands of different monomers to polymerize, but the methods we use to polymerize them create uncontrolled sequences. So we just get random conformations. We just get there's no higher order interaction between the chains. They just are a jumbled mess. But if we think about one of the polymers that nature makes, using proteins as the building block, it uses amino acids. It's got a very small library of monomers that it uses, but actually the machinery it uses allows for controlled primary sequences of amino acids, which leads to controlled secondary structures such as helices, and then tertiary structures, which is essentially protein folding, to allow for the creation of, using very simple building blocks, but actually by putting them together in a particular sequence, you can create functionality that we can't access with these random conformations. So as I said, nature does not have a polymer problem, we do. And a number of years ago, we started to think about, well, really why? And I think when we think about the key properties of nature's polymers, it uses stereochemistry. So this is the arrangement of this of some of the groups in space, allows for the organization of the chains to allow for these secondary and tertiary structures. We have specific sequence which allows for this particular folding. That gives shape and function. But the other thing is the monomer feedstocks that nature uses, such amino acids, are sustainable, and the polymers that it makes are degradable. Yet most of the polymers we make are not. So I think there's probably three key features that we've tried to embed in my research for a number of years, and that's around trying to think about how we can make synthetic polymers that have sequence, so they have added functionality and higher value. They're made from more sustainable feedstocks, and stereochemistry also allows us to access more advanced function. And I'm going to talk a little bit today about the sustainability element, yeah, and stereochemistry, because actually the approach that we've taken means they're interlinked. So stereochemistry. This stereochemistry is how atoms are arranged in space, and I think it's a good example. If you think about just the smells, R-limonene versus L-limonene, basically one smells of oranges, one smells of lemons, carvone, spearmint, caraway seeds. So exactly the same chemical structure, it's just the arrangements of atoms in space. And that's important from the example of oranges and lemons, but also biological effects. So nature uses stereochemistry and small molecules that are used either as drugs, and the stereochemistry is vitally important. And the good example is this phthalimide as a sedative, or a pterogen, or naproxen, which is not on, if anyone has bad back, they take naproxen, which is an anti-inflammatory. They take the S isomer. If they took the R isomer, it's poisonous. So stereochemistry is really important. And nature actually uses stereochemistry crucially in DNA. And one of the stereochemistry that's embedded within DNA leads to the structure of the double helix, which is a key part of the design, which then leads to the function. And we do use stereochemistry in polymers, and the example being isoprene, so natural rubber, so conventional, say a rubber band, is the cis isomer of isoprene, and this is elastic. If you just change to the trans isomer, so you just change the arrangement in atoms in space from cis to trans, you get gutta percha, which is brittle. So we know that stereochemistry has an impact on polymers. So stereochemistry is something we want to try and embed. Sustainability is the other thing that I think we want to try and embed. And this is a really nice figure, I think, taken from a paper from the Hillmeyer group in the US a number of years ago, that I think really highlights, I think, the challenge we have with the way we make a lot of our current polymers. And that's to say, the feedstocks that we use to make the polymers take millions of years to form. So again, if you think about it as from fossil fuels, they take millions of years to form. We then use those materials to make plastic bottles that we use for maybe a month, a day. It's again, the time scales are off. We use these the usable life, or the way we use such plastics, such a short time scale, that it then takes a long time for them to degrade to form feedstocks again and be able to close this loop. So the timescales of all these, be it the use versus the synthesis and formation, are all so much. These timescales are so much longer than the use. So I think it's important to think about the lifetime of making, using, and degrading the polymer. And the key thing is we need to short the timescale for the synthesis of the raw materials and the degradation. The particular material that we use a lot in my group is polylactide. And one of the reasons we like polylactide, and that sits up here, and this is a nice matrix that talks about basically how degradable the polymer is versus how renewable the feedstock is. So polyethylene is here, which is basically fossil fuels, all carbon backbone, very low feedstock renewability, and all carbon backbone. Polylactide is right at the other extreme, where we have some main chain functionality, so we actually have very good degradability, and the feedstock is from plants, so it becomes much. This is the area we like to work in and the material we like to use. And if I just talk you through the lactide cycle, so essentially lactide comes from the disposal of food and agricultural products, which you can reduce to starch. You can then hydrolyze, ferment, form lactic acid. You can then use that to polymerize polylactide to make products, then you can degrade to water, CO2, and again back to, so you basically you have this cyclic nature of PLA. And we can then, and the interesting thing is, so the degradation of a lump of polylactide takes about 3 months compared to 350 years for a comparable piece of polystyrene. So this really is starting to be able to degrade under much milder and much quicker conditions. And one of the big advantages of polylactide is that actually it also has stereochemistry. So this is the monomer and polymer structure of polylactide, and we have a stereo center with this chiral center. So that means we can start to now think about how that, and this very simple monomer that can be made from sustainable feedstocks, we've got chirality, which is one of the things we say we'd want because it helps us get added function. And this is just to give you, to just show you what the result of that. So really, I think very interestingly, this is we make the dimer of lactic acid, which is this lactide ring monomer, and we can ring open it, polymerize it to form polylactide. If we have one isomer, or the L isomer, we form a helix. If we have the D isomer, we form a helix as well. And these are opposite helixes. So these actually can form double helixes similar to DNA. If we have a mixture of both, we just form an amorphous polymer with no higher order structure. So we can by inspired by nature, by embedding chiral groups into our polymer main chain, we can start to form helixes and interesting morphologies of polymer chains, which rather than adding complex chemistries for this. So the interesting thing with these two polylactides is actually they're semi-crystalline. And what we've been trying to do with these polymers is use them to actually create nanoparticles that are of a similar size to some of nature's nanoparticles. And the example of that is, I'm going to show here, is this protein that assembles to form, this is a tobacco mosaic virus that forms this amazing raw, beautiful rod-like structure. So this is the scale bar. This scale bar here is about 200 nanometers. So these are about 1,000 nanometers in length, and they're perfectly well defined. And the stereochemistry of this building block leads to this beautiful rod-like formation. And viruses are a really good example. This is, we're all familiar with coronavirus, but viruses are a really good example of how nature uses assembly to make all different types of shapes. And the different shapes, the chemistry is quite, from a chemistry perspective, it's quite simple, but actually the shape can embed some really interesting properties. And we wanted to try and do that with some of our polymers. The way that we do that is by moving to more complex polymer systems where we take polylactide and add a second polymer. So we need to go to block copolymers, and the way that we do that, my group is going to demonstrate again, where we use again our controlled radical methods, where we have a capping agent in green, we add monomer units, the blues polymerize, then we add in a second group of monomers, which are now the reds. The reds keep adding to the end, and hopefully we will end up with two chains that now have a blue part and a red part. And the key thing is these two segments don't want to interact, they phase separate, and we can use that phase separation in something called self-assembly. And this is what nature uses to build a lot of its constructs. So this self-assembly essentially allows us to make all these different types of shapes. And the size of the blue bit, the blue polymer compared to the red polymer, basically determines what shape we get. We can get spheres, we can get rods, we can get hollow spheres. That's very well established. The really interesting thing with polylactide is because one of the blue block is semi-crystalline, we actually start to get, we can use crystallization methods to actually start to form some really interesting and quite different shapes. And that's what we want to try and do. And polylactide is a very simple, sustainable polymer, but the stereochemistry allows us to access some really quite interesting and strange shapes. This is really the only sort of chemistry slide I guess I have, but this is how we make our polymers. So we start off with this, what we call as our initiator. We polymerize in this hydroxy group to form, first of all, polymerize our lactide. So we have a lactide block. We then use this tricarbonate group to polymerize then the second monomer. So we end up with this polymer chain that has this short red block, our short polylactide block, and then a much larger dimethyl acrylamide, which is water soluble. And if we take this block, this polymer, dissolve it in water, heat it up, and then cool it down and allow it to crystallize, we can form all kinds of really interesting and different shapes from this one polymer by changing solvent, etc. So this just shows you some of the different shapes we can obtain, and we can make these lovely diamonds structures. And this is about 500 nanometers, this scale bar. So we make these big diamonds, these long rods, we can make hexagons, we can make just plates, we can make these weird kind of plates with hair, like hairy plates, etc. And all these morphologies all are as a result of the stereochemistry. Yeah, for very simple polymer, we can use crystallization and stereochemistry to allow us to access these really complex shapes. And what's amazing with these complex shapes, and it's one example of why I think nature uses such complex shapes, is that actually shape is really important when you think about the function of a material. And this is just the example of, if we take the same polymer, we assemble it and make spheres, and we use it. These are just gels, so calcium alginate gels, the sorts of gels that we use in biomaterial applications. We want to try and stick the two gels together. Yeah, so we have a gel, we stick, basically put it on as a liquid, so our polymer spheres in a liquid at the junction, and then stick them together, and basically there's a really poor adhesive. If we use exactly the same polymer, but we assemble it so it forms a plate, so it forms one of those diamond plates, we get amazing adhesive properties. So the shape of these polymers are having a really, really dramatic effect on their function. Yeah, so starting to think more like nature, where we're thinking about how we can embed complexity from shape rather than more complex chemistry. And these are very simple polymers, but with really quite amazing properties. And then just one of the last slides to show you the other thing that's, I think, is really interesting. If you take a sphere, compare it to a short cylinder and a long cylinder, and incubate it with cells, and we do quite a lot of, because we're interested in how these polymers interact with cells, they actually produce very different immune responses. So these are exactly the same material, but we've assembled them either in a spherical construct or a rod-like construct. And the cylindrical structure, the rod-like structures give a much more efficient immune response than a sphere. We don't yet know why, but it starts us to be able to think about actually the shape of the constructs that we're making could be really important in the way that we design rather than making more and more complex polymers. If we stick to some of the really good renewable and sustainable polymers such as PLA, we can use the stereochemistry to allow us to access different shapes, which can lead to really quite interesting functionalities. So that just brings me back to kind of I think these are some of the key principles that we should, I think, if we thought about sequence sustainability and stereochemistry more when we make synthetic polymers, especially with sustainability at its core, I think we would be designing polymers that would not be creating a polymer problem, and would give us would mean we would value the polymeric materials we have and make much more, and we would then not have perhaps some of the issues that we have today. And just to highlight that one of the things that we're interested in Birmingham is to look at the different recycling options that we might have for polymers. So if you think of the plastic waste, most of it, what happens is you get lost to the environment. You can also get mechanical recycling is a very well used recycling method, but it leads to a shortening of the chain, and ultimately they end up in landfill. You can burn polymers, which again is a good source of heat, but again leads to issues around environment and emissions. So we're particularly interested in areas such as chemical recycling. So can we chemically break down polymers and repolymerize them? And polylactide is an area that we've looked at in that. And also then whether we can depolymerize polymers and actually use them in a different, in an added value plastic economy, rather than just create plastic bottle to plastic bottle. Can they be upcycled into high value materials? So I just wanted to flag, one of the things I think in science that is hugely important is the collaborations. And this just is a slide of all the people that I have published with from all over the world, but in all different areas such as biology, chemistry, physics, engineers. And I'm really fortunate to have worked with some really amazing insightful and really exciting people. Some of these people, such as Helen here, graduated from my group and has now set up her own independent group. A number are academics here at Birmingham, and we have, so I think it's one of the things I think is one of the huge pleasures of my job, and amazing to have so many fantastic people to work with. That brings me to the end of my presentation. I'd be happy to take any questions you might have. Thank you.
Well, thank you very much for that excellent and really interesting talk.
Thank Rachel for that excellent presentation. Very clearly done. I particularly enjoyed the video clips your team had done with the moving around. It made it a lot clearer to visual. Well, for me, it's a lot clearer to visualize all the different things. So thank you very much. I'm sure the students found it very useful, very interesting, and stimulating. So thank you very much, Rachel. Yes, thank you. And we perhaps should also say this is the P.F. Franklin Memorial Lecture that is specially funded. It's part where we get our funding from, the Royal Society of Chemistry from, is the P.F. Franklin Memorial Trust. So thank you for doing this specific lecture as well. Thank you.